Kubernetes networking is just NAT and DNS. That's it. People give whole conference talks about the Kubernetes networking model, when really a service is doing what your home router has done for 20 years. I'm going to make that argument as hard as I can. And then I'm going to show you the dated, documented production failures that argument completely ignores. The devil's advocate case starts out strong. Kuberproxy's default mode literally uses iptables, the same NAT tooling as a home router. A service gets a cluster IP, and Kuberproxy writes a rule that rewrites it to a real pod IP. Mechanically, that is genuinely it. Here's where it collapses. Kubernetes' own 2018 engineering blog ran the numbers. 5,000 nodes, 2,000 services, 10 pods each, means at least 20,000 iptables rules on every single worker node, and the kernel walks them one by one per packet. That's not an NAT table. That's a linear scan wearing an API. IPVS mode replaced the list with a hash table, constant time, back in 1.11. And as of the February 2025 nftables announcement, IPVS itself is scheduled for deprecation, because nftables solves the same ceiling better. Just NAT does not get rewritten 3 times in 8 years. Fine, so the rewrite is real. But rewriting an IP is only half the trip. Once the packet points at a pod on another machine, Kuberproxy's job is over, and the CNI takes over the actual crossing. Some CNIs, like Flannel's default, wrap your packet inside another packet, an overlay, so the physical network never needs to know pod IPs exist. Others, like Calico in its non-overlay mode, skip the wrapping and speak BGP directly to your real routers, advertising pod routes like any other network. Same cluster, opposite philosophies, and NAT has no opinion about either. Next, surely the list of pods behind a service is boring. In January 2019, a Google engineer filed Kubernetes issue 73324 after a service scaled to roughly 10,000 pods. All those pod IPs lived in one single endpoints object, and that object blew past ECT's 1.5 megabyte write limit. ECT rejected the write. Request is too large. The watch on it died silently too. The fix, EndpointSlices, doesn't add features. It shards the one object into many, 100 endpoints per slice by default, GA in 1.21. That's an API redesign because one object physically got too big to save. Here's the one that should genuinely worry you. NetworkPolicy, the firewall object. Kubernetes' own docs say it plainly. Policies are implemented by the network plugin, and creating one without a controller that implements it has no effect. The API server will accept your policy, store it, list it in kubectl, and enforce nothing if your CNI doesn't support it. And for pods on the host network, the docs literally call the behavior undefined. You can ship a perfectly written policy that protects absolutely nothing, and no error will ever tell you. And the DNS half of just NAT and DNS? Every pod ships with a resolved unf you didn't write, 3 cluster search suffixes, and an option called dots set to 5. That means any hostname with fewer than 5 dots isn't treated as final. Look up api.stripe.com, 2 dots, and the resolver first tries it with every cluster suffix appended, several guaranteed failures against your own cluster DNS, before trying the real name, last. That one silent default is a structural reason why is our DNS slow keeps appearing in postmortems where the external service was never slow at all. Still think this is plumbing? April 2022, Datadog's engineering team publishes a postmortem titled, "It's always DNS, except when it's not." During routine rollouts, they saw error spikes that looked exactly like flaky DNS. The real chain, a gRPC reconnect setting made about 600 pods retry a dead connection every 300 milliseconds, roughly 30,000 connection attempts per second cluster-wide, with one deleted pod IP absorbing about 90,000 attempts in 90 seconds. The kernel's reverse path filter dropped the returning traffic as Martian packets, and the real bottleneck turned out to be Amazon's own hidden VPC connection tracking, not anything inside the cluster. For unrelated systems, one fake DNS symptom. Which brings us to the punchline. eBPF-based CNIs like Cilium don't make iptables faster. They route around the entire argument. Cilium's Kuberproxy replacement attaches programs directly to socket calls, connect, send, receive, and rewrites the destination before the packet ever enters the network stack all those failures lived in. Their published benchmark claims close to 1 million requests per second. Vendor number, take it as such, But the mechanism is real. Skip the layer, and you skip that layer's entire failure history. So, was the devil's advocate right? Is it just NAT and DNS? No, it's 6 layers, each one built, dated, and versioned because the layer under it hit a documented ceiling. A rule table that scaled linearly. A routing decision NAT never makes. An object that outgrew its database. A policy contract that can silently be a no-op. A DNS default nobody reads. And a cloud provider's hidden limit. Kubernetes networking isn't over-engineered. It's a history of incidents, wearing an API. Follow compile for what's under the hood.